of, it's not like true goal, but it is a symbolic goal that will help us to coordinate all efforts, is to arrive to such level when we will be able to describe dissipative quantum dynamics. So this is quite ambitious goal, and we do need to have foundations to do it. I know personally that a lot of class attendees do think practically and write competitive research papers, but there are two approaches. One is to do applied research, and another is to either just get refreshment of foundations and maybe plan on doing a little effort in improving and updating theories. So they're complementary to each other. And there are several, how to say, cornerstones, foundation, building blocks on which this quantum dynamics is resting. So basically what is assumed here is that we are, before now, in most or all of your classes, we were living under postulates of quantum mechanics, and we were living under big life quantum mechanics. We were believing or using it as that quantum state of a system placed, prepared in a state will remain there forever, right? And it is a postulate, right? And you know from your research experience and from common sense that it is a lie. So if you prepare a system in the excited state, it will relax sooner or later. And we do want to do mathematical treatment and sufficient foundations to describe it, how the state of quantum system changes over time. So there are several cornerstones. So one cornerstone is like if it is quantum dynamics of a system, which can be like single spin in the NMR, or it can be a couple of levels in a molecule that experience, like it can be donor acceptor state that changed due to nuclear motion, or it could be HOMO and LUMO levels that emit light because of interaction with bath. But a system interacts with the environment, it's not isolated, and absence of isolation is the major philosophical idea of the second part of the course. So we do need a Hamiltonian of system to bath interaction. System to bath interaction. So this is too general, and general thinking is not always constructive or working well. We may think of a little bit more practical aspects. And one practical aspect is non-adiabatic electron to vibration interaction. And I'm just doing it not as nice because I see how the camera is focused. And another one would be electronic system interacting with light, with photons. So basically, it is what I plan we should complete today. Knowledge or absence of knowledge of this time will, of this aspect will not affect the progress for the rest of the course, but it will create an excellent context. And a lot of past derivations were resting on these Hamiltonians. And if we want to be formal, rigorous, we do need to think. Another aspect that hello, London. Nice to hear that you are entering. So this is not a class on statistical thermodynamics. We are not going to do it, but we need to admit presence of this part of the knowledge, right? And it is needed because the bus that we imply always that our system of interest is always resting in the solvent or on a substrate or interacting with a pool of electromagnetic waves, is interacting with the bus, and one needs an average over the bus, right? So it is not a part of this class, but I cannot miss it and just make a little mark that CHEM759 used to have a couple of lectures on black body radiation, right? So it is an interface between electron to photon interaction and statistical thermodynamics, where you assume that there is a like box of modes of electromagnetic waves. They all are in a thermal states under Boltzmann distribution. There is a partition function, and when you merge it to electron to photon interaction Hamiltonian, you can reproduce sun radiation or tungsten filament radiation. So black body radiation. So basically what we get from statistical thermodynamics, we recognize that there is a procedure for making an average over ensemble. Okay. So what else we do need? If we follow this strategic plan and think how to address it, we can immediately recognize that if the bus contains too many degrees of freedom, it is something that cannot be solved completely. There is no exact solution. Like in some models where the bus is simplified, like a pool of harmonic oscillators, something can be done, but maybe not always. And one of the key concepts of the first part of the course was that there are only like handful amount of quantum problems that can be solved exactly, and the rest are approximate methods, right? So we do need an approximate method to deal with this infinite number of degrees of freedom related to the system to bus interaction. So you are already certified experts in which theory? Which was the last? You had basically three concepts in the previous part of the like adding addition of angular momentum, variational theory, and perturbational theory, right? So you are all experts in perturbational theory, but the one that you practiced was time independent, just to see how the energies and wave functions are affected if system is perturbed, if Hamiltonian has a small part which is foreign to the system. Now we again have perturbation theory, but we add that it will be time dependent perturbation theory, and we need it at least up to second order. There. So it is another component that would help us to get to dissipative dynamics of a system. And it is a way how we take Hamiltonian, we treat it via perturbation, and then we add the average over ensemble. So it is a contribution, and it gives us a strategic plan. So after I finish this diagram, we'll chop it on pieces and divide by number of days we have, and just slowly move through material. And it will be like a regular course with some normal foundations for quantum theory and physical chemistry. But now we will have a little strategic plan of what to do with it. So the interaction between degrees of freedom of different nature sometimes happens on a very quick time scale. This is especially recognized if one deals with UV visible absorption, where the frequency of oscillations of electromagnetic field is shorter than a femtosecond, or of the order of femtosecond. And if one wants to predict some dynamics where levels are populated, shorter than femtosecond dynamics is quite hard to follow, right? So one needs a trick that saves us from following dynamical processes on a too short time scale. And this would be so-called rotating frame. There are more sophisticated names for it. I'm just trying to be simple. Basically, in abstract space, if the accumulation of phase by a quantum system and rotation of oscillations of electromagnetic field come with the same frequency, one can do some tricks to cancel these oscillations and get a small, slowly changing component. So the idea is simple, but we would need to devote like a couple of lectures to be practical, and maybe 1 or 2 MATLAB meetings at Wednesday evening. I believe that in this class, first part, and in the CHEM759, there was a brief mentioning of the Bloch sphere, of the sphere where a state of a spin is drawing a trajectory of a pedestrian on a globe, right? And applying all the things to practical degrees of freedom, to practical problems, would kill the course. One cannot apply all advanced concepts to complicated practical applications. Therefore, to finish in time, we need to select the smallest or simplest possible applications. And simplest possible application is two-level system, like 2 electronic levels, which can be either spin up, down, or homo-lumo of a molecule or an atom. And if we get through all this machinery and learn the foundations, and you decide that it is your path of your life, later on you can apply the same concepts and redo them, rewrite them for more advanced systems and be happy. But to finish by the end of semester, we will be very, how to say, boring, limited in the applications. No quantum dots, right? No meta-organic complexes, just abstract two-level system, but it will keep us busy completely. So two-level system, two spins, surface of a sphere, right? It is what was mentioned in previous part of this class and in the other class, right? There is an observation that if a spin is thermalized, right, then instead of pointing a trajectory or a point on a surface of this sphere, it will dig deep which please raise hands if anyone against this plan. No one. It means everyone approves it. Okay, and now since everyone approves it, we need to do our little contributions to do it. So please get acquainted with this list, and here are the concepts that I will fail to show in a reasonable time. So I need your help to me and to your grades of making choices of what you could present in like in about 2 weeks. And I will explain what are these materials and how to deal with them. So it is intended to be much, oh, yeah, thank you, much shorter and simpler. You don't need, but you can if you want to. Or, oh, you got one. Okay. So let's mute microphone for a second. So that I'm going to present is borrowed from the. Yes.
From this list, we have the sublist like 2A, B, C. You would still just pick one of those subtopics.
Well, I understand that plans are more ambitious than we can ever do. Ideally, everything like 2A to B to C to D to D to E could be one presentation. But if you think it is too much, you can select more than one subjects or less than 5 subjects nearby and select what you would feel comfortable to present in 2 weeks. Okay, and maybe let's make you can make choices personally, and then I will do a little blue, not blue moon, blue star. Maybe I should do blue moon. And there, and I let this little copy to go around, and you select what you prefer at most, or what you hate at least. If this time I start with Adam, next time I will start on the other part of the class when we get another. Ideally, we should cover everything from the top to the bottom. The applications, like three bottom things, are not as needed because they were presented 7 years ago in the same course, and they are applications rather than foundations. But foundations should be covered if possible at all. Okay, now I'm going to. Do I have a permission to erase this little diagram? Anyone wants to see it for longer, or is okay? Okay, no one wants.
I have like an actual eraser too.
Huh?
Instead of right.
What?
I have.
Oh, thank you.
You'd rather have an actual eraser.
Okay, yeah, I'll use it next next time. Thank you. So last time this course was taught 7 years ago, and formally in the syllabus that you've got, it is time to go to time-dependent perturbation theory. That you probably have seen one slide about time-dependent perturbation theory in the slides from London, whatever, 4 days ago. basically, he covered everything what I have to cover in 3 lectures in 3 minutes. I will just choose material a little longer, but we will go through it. Do not worry. But as soon as we go through time-dependent perturbation theory, we immediately come into idea that we need to apply it somewhere, right? And there are several applications with mostly popular where it's major. It's like maybe 80% of effort of applying time-dependent perturbation theory is interaction of light with matter, is when one has emission or absorption or stimulated or spontaneous emission, like Einstein coefficients. So in order to describe application of perturbation theory to light to matter interaction, we need to have an idea what is light to matter interaction. And in standard chemistry textbooks, it is just written as interaction is equal to minus electric field times dipole. And that's it. My goal for remaining hour or so is to provide as much as possible details behind this simple expression, right? So one can intuitively agree with it. Like if there is a electric field, there is a dipole consisting of positive and negative charge, it will just rotate it. If it is rotated along the field, the energy will be negative and minimalistic. If it is against, it will be maximal. If it is perpendicular, it will be somewhere in between, right? The way how the many equations are processed and derived in the literature related to the subject look a little bit different. So if you close your ears, close your eyes, flip back and sleep, you will not lose anything in the course. You'll be able to succeed in the rest of the program. So it is more like decoration and a little fluffy addition. But if you do listen and follow, it will create a little bit more foundation towards this equation. Okay. So I will probably get a little interview and help from physics majors because I've got my basic education in this like too many years ago, and I can do many silly mistakes. And some who took it recently may immediately find errors or just help with definitions. Unlike regular courses, regular classes that we will have in the future, where there will be a single idea, then 2 hours of derivation, and then analysis of the result. This one will be just a mostly collection of definitions, rather than long with very few derivations. But it will create a context for our future activity. So, what is electromagnetic field? You can raise your voice and speak if you want to. So by it's like light, right? And it is electric and magnetic. And electric and magnetic field are created by static and moving charges, and it propagates and even can exist in the space without charges, like propagating wave in form of photons, right? Who was Maxwell? Or just in related to electromagnetic waves? Just raise hands if you've heard the name of Maxwell. Okay, everyone, right? So what are Maxwell equations? You don't need to comment and write down. Just raise your voice if you can tell in 3 words what it is.
They basically describe electric and magnetic fields.
Okay, yeah. So we do not have discrepancy. We all agree on this, right? There is electric field that is created by charge and acts on charge. There is a magnetic field that is created by moving charge and acts on moving charge. And they are typically referred by like letter E and V. And there are differential equations that show that they interact, they like pass energy from electric field domain to magnetic field domain, and they can propagate. No one objects, right? Vectors means that at each point of space, there are 3 numbers. So 3 numbers for electric, 3 numbers for magnetic, already 6, too much, right? So there are abstract derivations that are very popular in the literature that refer to so-called vector potential. Raise hands if you've heard and you're comfortable with it. Okay, so basically one by applying some differential operators, one can take vector potential with only 3 components and extract both electric and magnetic field out of it, right? So magnetic field is cross product of the vector potential, and electric field is speed of light derivative of time of vector potential. And you can see that likely those 2 are collinear, likely these 2 are perpendicular in a local point. So it is only a convention for lazy people, instead of 6 numbers to keep 3, right? There is a scalar potential, which is a regular potential that attracts electrons, but if we have a free space without charges, then scalar potential can be skipped for a time, and vector potential is enough. There is a concept. So as you see, if objects that can be measured in the physics lab are generated as gradients or as differential operators of this vector potential, if one adds a constant, observations will not change. So subjects for presentations. So way how to select this unknown indefinite constant. Okay, now we do have propagation of the thank you so much. We do have propagation of electromagnetic radiation in space, and the standard way is to set up the propagation of electromagnetic wave through equation for the vector potential, and as soon the solution is found, one can reconstruct electric and magnetic field backwards from vector potential. So gradient squared of vector potential. Now I need a help from professional physics majors to confirm that there is a minus sign here. I'm not 100% confident. 1 over c squared d2 dt squared of a. So what can we say while looking on this equation? Which I know that maybe no one of us has pleasure or positive emotions by looking at equations. It's not this activity that we prefer. We better look at the art or motion picture or just on a glass of beer, right? But if you need to analyze it, what do we see and how do we compare it with let me write it in a slightly different order. I put this thing on the other side, gradient squared, a squared. And here for comparison, I would put d dt psi minus I over h bar gradient square plus potential psi. So what do you think while looking and comparing these two equations?
The top one sure looks an awful lot like the Schrodinger equation without any potential.
What about the order of the time derivative?
Oh, I suppose, yeah.
So they both have special part, special, not like you're so special, but in space derivative, and they both have time derivative, right? But they have different order of derivative. And if we would add one more equation into here, then someone who is or used to be major in math can say that partial differential equations can be characterized on elliptical, parabolic, and hyperbolic. Not hyperbolic. Hyperbolic. Okay, so elliptical, parabolic, and hyperbolic. So by comparing the order of derivatives and their mutual signs. So, and this is Laplace equation for electrostatic field. Okay, so different order, but since they both have dependence on time and space and derivative over both, likely there will be wave solution, right? Like the one is drawn here. Something that will go like E momentum position minus frequency times time, right? Or superposition of such solutions. So something will move forward. Okay. So in free space, the vector potential can be set as amplitude, then polarization vector, and polarization vector is orthogonal to direction where it propagates. And because of gauge that I want to skip, and someone already know who, or Tori decided to speak about it. There is two opportunities to select the polarization vector. Polarization vector. If you ever did some practice in optical laboratory, in laser lab, there are like lasers, polarizers, which can be for linear polarization or circular polarization, right? So polarization is what defines the orientation of this electromagnetic fields in space. So, and then we can just have plane wave exponential I k r minus I omega t, where omega is like frequency of light if it is light. No objections yet. So it's like if it is wave equation, it should have a wave solution. If we want to be a little more practical and related to real life, we can add the stuff that propagates in the opposite direction or goes backwards in time. Exponential I k r plus I omega t. And then we can put the special part outside of the brackets, and then cosines, then the exponentials oscillating with different signs will add together, and by Euler equation will give either sine or cosine. If it is plus, they will give cosine, right? And it shows that just propagating electromagnetic field in a form of vector potential will just perform cosine as function of time, and we'll have this oscillations in space as well. Okay. So we do need to get a little bit of intuition of what is vector potential, because by now it is an abstract concept. There are no, well, almost no instruments to measure vector potential. Typically, instruments generate and measure electric and magnetic field, right? And we may need to generate an image or verbal formulation of how to interpret like amplitude of vector potential, a little bit more than this equations for connecting electric, magnetic, and vector potential. So I am going to follow the following plan. Define what is power density and energy density, plug in this vector potential into conversion it into magnetic and electric, compute power density, maybe skipping some derivations, and then it will give us the, I wouldn't say visual, but it will give intuitive interpretation what is vector potential. And I don't have patience to keep it as an intrigue, but the answer will be that square, absolute value square of wave function is probability of electron to be somewhere. Square of absolute value squared of vector potential will be number of quanta in a given volume. And we do not need more than this verbal statement, but I will torture myself and yourself and just provide some additional background for this statement. And probably I will use my thin cheat sheet. So who pays electric bills? Okay, so if probably we just read the monetary part of electric bills, but sometimes we see what is written there, and it measures power in which units. Okay, right? You wanted to say different?
I feel like it was like kilowatt hours or something.
Okay, I thought megawatt. Then you have a powerful house. Okay, and what is what? What is power? What are units of power? What's mean?
Joule per second.
Right, energy per time, right? So if you do have, I'm just trying to navigate so that it's okay. So the power is joules per second or energy per time. So if you do need the energy, we will just integrate power or time. And if you need average energy, we can like divide by integration time. Probably it is what Excel Energy is doing when they want to predict their spendings and their income. Okay. Now I'm going to declare a couple of things that would took a couple of lectures if it would be a physics class. And those physics majors, please catch me on any errors so that you will not have errors left in our heads after the meeting is done. So if we solve the wave equation for vector potential and convert it into electric and magnetic field, or if you solve generic Maxwell equation, we will have this orthogonal waves propagating, right? And definitely electromagnetic waves can transfer energy. One can burn paper by magnifying glass from sun. One can, well, we do not have laser pointers that put things on fire, but hypothetically it is possible, right? So it definitely transfers energy. And there is an experiment where one has a vacuum tube with black and reflecting petals, and when one puts it on the sun, it starts rotating, right? Because reflecting and absorbing has different pressure. So when electromagnetic wave is propagating, it carries some energy, some power. Likely, intuitively, the power is transferred in the same same direction where the wave is propagating, the vector k in there, right? So we have electric field, magnetic field, they are orthogonal, and there is k which is orthogonal to each of them, and we anticipate that energy is transferred in this direction. By now it is hypothesis. I will not step too far from it, but if one goes systematically through electrodynamics, there is so-called pointing vector. So there is Y not I, so it's not like pinpoint, but it's a name of a person. And in Eastern Europe, there is another scientist who derived it at the same time. And it tells that if one defines it as a vector product, as a cross product of electric times magnetic field, it will correspond to the wattage, to the power density of electromagnetic radiation, and will show the direction where it goes. Like cross product E times B will coincide with this direction. Suppose we do have like a screen, and we do have several electric and magnetic field do depend on position in space. So it will arrive, we will hit screen here, E, B, RT, and we have another part of wave that comes electric, magnetic. It hits maybe with the same or different amplitude. So if one chops the surface on little segments and assign each segment with a normal vector, maybe let's dn for it being very small, then the surface integral over this area of screen of the power times normal to the surface will give the total power transferred through the screen. Catch me if you can. I don't mind making errors, just care that they will be corrected. So E cross product B to the normal to the surface. And there are chapters of electrodynamics that show that this expression can be converted from surface integral into the volume integral. And upon the conversion from surface integral to volume integral, instead of cross product, one would get E squared plus B squared. So right now, I'm just inviting all of us to believe it or provide justification if you saw it in the past. Did you? You're just nodding like, oh yeah, sure, I was deriving it yesterday.
It's one of like Green's theorem or Stokes theorem or something.
Right. Would you approve?
Yes.
Okay. Yeah, thank you. So what we would do if we want to, so the little goal in the next, whatever, 10 minutes is to agree that the meaning of the vector potential or vector potential squared is number of photons per volume, right? And we do not need nothing than this sentence. I'm just torturing myself and yourself by having this statement very solid. So if you want this statement to be very solid, we need to take this power per volume, and we do need to integrate it over time. And then we'll have power, not power, energy density, like how much energy is stored in a volume through which electromagnetic wave is passing. So on one hand, we will practice this one over T dt W, or W is taken from here. On the other hand, we can intuitively tell that this will be the number of quanta times energy of omega, big omega here. So energy stored in the volume in a box if it is occupied only by monochromatic light, only certain wavelengths. If one needs to generalize, one can do summation over different frequencies, wavelengths, but it's good. And then by processing this expression and plugging it into here, you will see that it will be some constants times E naught squared equals to number of quanta h bar omega. And then you'll see that constants will include volume, and we will just solve for A naught. But as of now, I want to torture myself by finding this constant. So I remember, please do not move. Let's keep it focused in here. I remember that in the first part of the class, you had a tradition of a break. So I think I will try my best to complete this little derivation. Then we'll do a little break, and then I will go to second part, which likely will have a little bit more fun, because this is more like a set of definitions rather than a story or derivation. So E equals -1 over C dA dt. So -1 over C, and then we had there A naught polarization vector, and then we have time derivative of the E I chi AR plus I omega t plus the same EI KR plus I omega t. So by taking derivatives over time, we just reproduce exponential and get the factor in front of time into there. So -1 over C, E naught polarization vector, I minus I omega, I R minus I omega t. And here we'll have plus I omega E I AR omega t. So if you want to practice Euler equation, you'll see that because of this minus cosine will turn into sine, but basically it's same frequency trigonometric function. And we get that up front, we got this frequency, speed of light, and initial amplitude of vector potential. If you want to do the same for magnetic field, I did this exercise at home, but if we will do it right now, we will ruin the rest of the class. The trick that by taking this derivative, one would get a vector here onto polarization, and then a naught, and then the exponential functions. It is a pleasant exercise that I suggest we skip, because the energy contributed by electric and magnetic field will be the same, like half from here and half from there. So just to save time, I will process electric field and invite you to believe that for magnetic field will be the same contribution or level of contribution, but it's like a couple of pages of derivation. It's a little less pleasant, and one needs to do this definitions of the cross product with determinants of 3x3 matrix, right? So we are doing average energy as so the integral over volume, and then integral from 0 to, let's say, integrate over one period. Will be from period is inverse of frequency, and then if you do this 1 over t, then it will be frequency over 2 pi. And then we will have whatever we get from electric and magnetic field. So A naught squared, C squared, probably will be a minus because of this I, omega squared. And then here, this one will give us sinusoidal function squared, sine squared of omega t dt, and there will be another factor of 8 pi, and then we will have another factor too, because we double this. So if we change a variable like dt is omega t divided by omega, then limits of derivation will be from 0 to 2 pi, and integral from 0 to 2 pi of sine squared will be one half, right? So it's a median. It oscillates between 0 and 1, and by taking error, it will be 1/2. If you find it different, let me know. We'll correct these recordings. Okay, and then we just extract all constants from here. So energy density is volume. So my only goal is to track and cancel constants. A naught squared, C squared. Probably there is a minus. omega squared. Now we have 1 divided by omega because of the change of integration variables. And we do have 1 over 8 pi 1/2. So one can likely cancel this omega, and I'm going to erase the space because we need maybe only 1 line to complete this exercise. So energy is volume, A naught squared, omega squared, speed of light squared, and then some collections of pi factors. Something like, I don't know, 16 pi. Or maybe 32 pi. I will not fight for it right now. And we assume that it will be number of quanta times the energy of 1 quantum, right? So if you want to solve for A naught squared, we will have this frequency will cancel this frequency, and so number of quanta per volume, and then the rest will be h bar squared, speed of light squared, several pi constants. Divided by omega. And if we need an interpretation of the vector potential amplitude, we just take square root of all this combination. So number of quanta per volume, inverse frequency, h bar c or pi. So the reason for this exercise was just to confirm verbal statement that the meaning of amplitude of vector potential is a square root of number of quanta per volume. So if we ever see vector potential, we shouldn't be scared off and, oh, okay, if you know number of quanta, we know what it is. Or we, in the thing that I do not want to touch right now, otherwise we will have our minds blown up. There is a second quantization of electromagnetic field, which replaces the vector potential by creation and annihilation operators, which will also able to generate number of quanta. So if one does like Jenks-Cummings model and things like that, one does need to practice it every day. And I think it is time for a break.
Oh, we have it here.
Oh.
Okay. You will have a break.
We have a break right now.
Ah, okay. Then I will give you the exams back. And you before your breaks, right? What are your exams?
So break for whatever, 4 or 5 minutes. Right?
You have any idea why this is?
No, it's not.
Maybe it's too intense.
David, you forced you to sit in the ground?
Yes.
Because in my class, you put it there.
I've asked David to help with setting recording. I hope the news that you're getting in the mail are positive.
And you have to schedule your exam sometime, right? I'm not going to do it. It should be your initiative. So why me? Ask me. What kind of event? We have 11 children. We will have students again, high school students coming or visiting with us. Most students, because one will be our regular students. Most of them have a major in biochemistry, so I will be busy with them. Maybe then 1 p.m. 12:30 or something, huh? Anytime Friday? Yeah, so then let's put it maybe, and one was 1 to 3 then, right? Yeah, 1 to 3. And if you come a little bit further, it's also. And overall, so it sounds really good. I think most of you are in the age, somewhere in the range, low B. There is no C here.
Thank you. You okay?
Number 1. Yep, thanks so much. So perturbation is electric field times dipole, and there is an alternative way for this equation, which looks very crazy. For if you saw it, you'll find it natural. If you'll see it for the first time, I think you will be surprised. So kinetic energy of a charged particle in the electromagnetic field, generally we expect that we have momentum squared over 2 mass, right? And if it is going inside the space with vector potential, then the momentum is modified by vector potential. So vector potential modifies momentum of a particle. So these two equations are a little unlike, but they represent the same thing. And for the success in the class, only top equation is needed. The rest is just that you feel comfortable in the literature if you ever get to do this as your professional activity, right? So if we open the brackets, momentum squared 2 masses minus, now one should be careful. So P E C P times A plus A times P. because we are entering the quantum area and we do not know if we are allowed to swap the objects. We better open them in a safe way. Plus E squared, C squared to masses, A squared. So there, I don't remember if I put it as one of the, maybe I did, and someone already selected. Yes, I think the closest is Steven. He selected 3C, but it is 3A. So criteria of small field versus strong field limits. So the number of quanta per volume can be really huge, or can be like half of a quantum or 1/3 of a quantum for like, can be a really small amplitude. And if the A naught mathematically is substantially smaller than 1, approaches 0, then A squared will be smaller than A, right? And then the last term can be dropped. So when last term is dropped, it is a small field approximation. It is valid if you do linear absorption or emission spectroscopy, and in most of the everyday activities that we practice, it holds. So up to maybe 10 or 5 years ago, most people were practicing only small field approximation. If we are little dwarfs who crawl into inside area of a laser, we will find out that this doesn't hold. So inside the resonator, inside of laser, the intensity of vector field is substantially bigger. And if one wants to do something inside a cavity, this is not a good approximation. So strong field approximation. So, and I know that it is what Patricia is doing. And there are quadratic terms that one doesn't drop. So it is related to mutual comparison of this parts. Now, for the class, we admit the small field approximation. What do we do with this combination of A and P? We need to return to the word gauge. And the gauge that likely will be presented by Tori. If one looks into Wikipedia, there are like about 6 fancy exotic gauges mentioned, but most popular and used here and in for simple guys is Coulomb gauge, where one applies the condition that dot product of the gradient and vector potential is 0. So if we apply this condition, we can simplify the expression on the top. So the momentum of the charged particle should be thought as derivative over space, a gradient, Planck constant, imaginary unit. So should I put minus or should I not? Minus? Thank you. I am pleased to be in the surrounding of educated people. Now we can plug it in and just practice this this little expression. See what happens. And after we combine this combination, this definition of momentum and the gauge condition, we can return back to momentum. So we temporarily go into the space of differential operators, and then we return back into symbolic notation. So P A minus I H bar gradient dot A plus A dot minus I H bar gradient. So to carefully process this expression, I do not dare immediately cancel this one or put it to 0. I need to process it in the same way as one plays at the basic quantum mechanics while introducing commutations. So for any differential operator, we should assume it acts on the unknown function. Second term, we have gradient right in front of a function, so we do nothing. First term, we have gradient applied to both vector potential and the function. So I better work carefully and open the brackets. H bar gradient times A times function unchanged minus I H bar A times gradient applied to phi plus vector potential minus I H bar gradient phi. So due to gauge, we can drop the first term here, right? But it's good that we do it only now, because before this expression contained another term. And due to this derivative of product of functions, we do see that these two functions are identical, and we just have a factor 2 minus 2i H bar A gradient. And then after we are done with derivations, we do not need to keep this unknown function, and we can return back to the notation of the momentum. So we can do it as 2a times b. So this little trick is available because of the selection of a gauge. E squared over 2m minus charge, mass, speed of light, and I can put 2 and 2 which are cancelled, right? Then we do have vector potential times momentum. So this is kinetic energy, which includes, it is modified due to presence of electromagnetic field, which we treat through vector potential. If you want to have the full complete Hamiltonian, we would admit that in addition to kinetic energy, there is a kinetic plus potential, right? So we will have E squared to m plus v of r, and then minus E mc dot product of vector potential and momentum. So this combination of energy terms can be treated as unperturbed Hamiltonian and perturbation, right? So the perturbation or interaction of light to matter is reasonable under the small field approximation, can be written as charge, mass, speed of light, vector potential, momentum of charged particle. Okay. So modified momentum, weak and strong field. Now we need to focus on the long wave approximation. Everything that is provided at today's lecture, I wouldn't say garbage, but it is, you can survive and succeed in the course without this information completely. But it gives a little grains here and there, like long wave approximation is our path, is our foot into the door to different exotic spectroscopies. Right now, we are thinking only on the most primitive linear absorption and emission. But what about Raman scattering, relay scattering, two photon absorption? So transition to these exotic spectroscopies is what we can do next. And it will be done. So for our primitive linear absorption, we will admit so-called long wave approximation, but before we will process this equation with a little bit more details, and we see a path to exit primitive spectroscopies and go to advanced spectroscopies. Okay. My thin cheat sheet. So light to matter interaction minus, let me practice my memory, charge, mass, speed of light. What else? Did I miss any constants? Not yet. Now we do have a solution of the vector potential in a free space. So it is A naught, which we already know, right? Amount of photons per volume. Polarization vector. And then we do have e to the power I k r plus I omega t e I k r minus I omega t. And here we can rewrite it as a node polarization e to the power I k r outside of the brackets, and then times 2 cosines of omega t. Now we do plug this expression into the light to matter interaction under weak field approximation. Small field, weak field. So V equals minus E MC E naught polarization exponential I K R times E times 2 cosine omega t, uppercase omega t. This K is the wave vector, and we can rewrite it if you want as the momentum of light. So this is momentum of electron, and this is momentum of photon. Momentum of light over h bar, right? Or we can rewrite it as 2 pi over lambda, right? So here we do have two momenta. Momentum of charged particles like electrons, and momentum of the photon. it looks like a simple equation that one cannot simplify or make more complicated. But there is a standard procedure that is allowed always. So function can be expanded in Taylor series, right? So we can replace the exponential as right in power series. And we can rewrite this expression once again. So V equals minus E MC A not E polarization vector times 1 times momentum of electron times cosine omega t. And then the next term was E MC times I MC A not polarization vector A R times momentum of electron cosine omega t. Plus continuation. So the meaning of this wave vector is 2 pi over lambda. So if we keep only the first term, we will have polarization vector and momentum and nothing else, right? So it will be linear in respect to momentum of the field. And this first term means that product of wave vector times selected direction in space is negligible. Mathematically is okay, but it doesn't impress me. It doesn't give a visual picture or any reasonable analysis. But if we look at this, if you just look at this series as 1 plus I 2 pi lambda times R with absolute values if it is projection. So the changes in properties of molecule as from the beginning, from the tail to the end are small. So if you drop this term, are small in comparison to the wavelengths of light. So size, linear size of atom or molecule, or of atom, it's definitely of molecule is negligible in comparison to wavelengths. So what is the size of a quantum dot? Of your quantum dot? So how many nanometers?
It's like 5 or 6.
Okay, on experiment and 1 in simulations. Tori, what's the size of your metal-organic complex? How many nanometers? Very approximately. Or how many angstroms? Angstrom, very roughly, it's 1 bond length. How many bond lengths from tail to the end? Oh, 5-ish, 10-ish, right? So 1 angstrom is 1/10 of a nanometer. 10 angstroms is 1 nanometer. So your molecule is 1 nanometer. what is the wavelengths of the visible light? From okay, 400. So what is bigger, 1 or 5 nanometers or 500 nanometers?
500.
Okay, so the ratio of the size of the molecule divide by lengths of a molecule divide by wavelengths of light is about 1/100, right? So it justifies to drop all terms except the first one. And it is because the wavelengths of visible light is so much bigger than the size of the objects we typically deal with. If you go to favorite subject of Patricia, if you go to infrared, it has wavelengths of like 2000 nanometers. It's even better, right? But if you go to UV or shorter and shorter wavelengths, then it will be problematic. Or if you have conjugated oligomer, which is 100 nanometer long, then variation of electromagnetic field from beginning to the end of a molecule will influence its optical property. So if we, in this course, we will stay within long wavelengths approximation. But if you go further, then one would need to explore how the properties change. Like if you do some matrix elements, it will be additional terms that will show variation through the lengths, and they will give additional properties. Sometimes people take this term right away. If matrix elements of the lower term are completely zero, if like molecule is absolutely symmetric, unpolar, and doesn't absorb light, selection rules show that first term doesn't give any transitions. Then one needs to go to the second order. And there are this approximation, or abandoning this approximation, gives a path to spectroscopy's past linear absorption and emission. Okay, so we are done with long wave approximation, and now we do need, I think, last task for today's meeting. Okay, 24 minutes until 4. I should finish maybe in 4 minutes, but we will be kicked out in 24 minutes anyway. So a lot of us do perform practical computations. I think everyone except Max. Maybe Max also. Did you practice Gaussian software as a fun? So there are computational software where you put as an input like structure of a molecule, and as an output you get absorption spectrum. And their absorption spectrum does relate to concepts of transition dipole and oscillator strengths, which all follows this small field and long wavelength approximation. But those of us who practiced, who were providing equations to justify this absorption spectrum, or to like do additional derivations or looking inside the code, notice that typically one is thinking about optical properties come from matrix element of transition dipole, of the dipole, which is like positive and negative over some distance, right? But there we see that it is product of vector potential times momentum instead of dipole, right? So to achieve sanity of our minds, that all our previous careers are valuable, shouldn't be thrown away. We need to find a path between electromagnetic interaction in the momentum representation and in the dipole or coordinate representation. So it is something that I want to go over. So I'll keep maybe this one. and check that so, and right now we do have minus EMC. E naught polarization vector, momentum of electron, and I hope and believe that's it. Assign omega t. So we got rid of this oscillating waves in space, right? Basically, we can think that inside an cavity, inside mirrors, the vector potential or electric field, which is proportional, and we sit our molecule so small that change of the field on the length of a molecule is negligible. It can be considered as homogeneous. Now, to practice transition between momentum and position, we need to depart. Do not move. I'll continue there. Thank you. We need to depart from the abstract operators and go to matrix elements. There is a necessity and benefit of it. So if we assume that we go from specific initial to specific final state, we will be able to practice commutation relations, and we would be able to introduce the Hamiltonian, unperturbed Hamiltonian, get some benefits out of it. Right now, you probably do not believe, or what I'm saying is not convincing enough, but going into specific matrix element allow additional chance for improvement, for more optimal derivation. So instead of V, we are going to look for transitions between eigenstate M and eigenstate K of this matrix element. If we want to follow notations, I do not take credit for designing all these equations are known. If you want to admit notations of this book, I'm not approving, but I'm following. By some reason, the letter V converts into letter U. So I would keep the letter V, but it is what they use if you are going to look into that book. So M and K are H unperturbed Hamiltonian acting on the state M, gives state energy M and reproduces state M, and same for K. So basically what we are going to work with is minus E MC A naught realization vector, and then matrix element M E A. So we just look into matrix element of momentum operator in basis of eigenstates of Hamiltonian, or unperturbed Hamiltonian, where H equals, I just reproduce E squared to M plus potential, like attractive potential that electrons sit near ions in our molecule or quantum dot. H naught plus this interaction Hamiltonian. So there is a trick that I will borrow from the cheat sheet. I skipped some fun pictures, but remind me about fun pictures if you have a couple of minutes at the end about Aronov-Bohm justification of light to matter interaction. Very careful. Letter by letter. So if we prove that this relation is correct, then the plan is as follows. We will plug it into there, convert operator of Hamiltonian into energies of eigenstates, and convert momentum into position. And then we will arrive to the dipole interaction. Make sense? So again, for success in the course, you just need to know this 1, 2, 3, 4, 5 letters, right? But this gives a little justification and chance to swim in the literature, because the authors do not promise to stay within one or another. They randomly jump from momentum to position representation between vector potential and electric field. Okay, I do not have steam to prove it in 3 dimensions, but at least if we do it in 1 dimension, it probably can be done. So h bar commutation p squared over 2m plus v. Let's do only px, otherwise it will be too much, and we will believe that it will be the same for other dimensions, and one can do a vector thing. So commutation of any power with lower power of the same variable is always 0. For this reason, we can remove the potential and look only onto commutation between momentum operator and momentum squared and position. And we are processing U sub mk. No, we are processing px. Okay. So I am h bar to m, they immediately cancel. And here we have p squared x. Let's replace p with minus I h bar ddx squared x. So I h bar minus h bar squared d2 dx squared x minus x d2 dx squared. Extra credit, respect and honor to anyone who finds errors. Now, if we process this commutation relations, it's a healthy trick to assume that there is an unknown function in here, right? And we do see that here differential operator acts directly on a function and nothing will be changed. But if we look onto the first term, we do need to practice derivative of a product function. So let's do it carefully. Factor 2. And now we do have, we put one of the derivatives outside of the brackets, and here we have d dx of x times phi plus x d phi dx minus x d2 phi dx squared. So derivative of x over x will give 1. So it will be phi. And here it is what it is. Let's go to the next line. H bar 2. Now we have ddx of phi, so it is unambiguous. And then we apply ddx to the second term. ddx of x times d phi over dx. And everything is, we are subtracting x d2 dx squared of phi. I didn't put anyone asleep yet. So few more brief steps. X. And here we have dx dx times d phi dx plus x d2 dx squared of phi minus x d2 dx squared phi. So yeah, this will be 1. First two terms add together and provide 2 d phi over dx, and second two terms subtract and give 0, right? So and now we can, and let's cancel factor 2, and now we can track back and redefine derivative in this factor as a momentum. So it's I h bar ddx. I probably lost minus somewhere. I stop writing the unknown function phi, and I tell that it is px. Momentum may have been lost somewhere, but minus sign. But you see that we basically prove this with a precision up to the sign. So if we believe this expression, we can just calmly replace momentum operator in the matrix element of light to matter interaction and see what happens. Okay. Yeah, I think we will finish in time. Are you just going to start, set, go? I think the rest of the lectures will be a little shorter. This one is new and was not included in when this course was delivered 7 years ago. It is completely new. So U M K minus E M C A naught polarization vector M. And now instead of P, I put I M H bar H naught R. A here cosine omega t. So opening the commutation once again for in this expression MC A naught polarization vector M. Let's put factors up front. M H bar M H naught R minus R H naught. So here we can treat it as two terms. M H naught R K minus M R H naught K inside these brackets. Here, if Hamiltonian acts on a ket, we are getting eigenenergy of state K, and state K is unperturbed, right? So we get M R times EK K. Here we can practice liberty and apply since Hamiltonian is like Hermitian with some symmetry, we can like a matrices, we can apply it backwards, acting on a bra. And it will be same bra and replacing Hamiltonian to the eigenenergy M. M operator R, A, the bracket. Now we do not have operators anymore. Here and there, we do have matrix element of position operator, right? Not momentum anymore, it is position. And we can take the energies, EM and EK, as the only thing remaining in a bracket, EM minus EK in a bracket, and the matrix element of the position can be taken outside of the brackets. And then we just carry on the so the energy difference is the same as frequency between transition frequencies between state M and K. And if we are considering resonance condition, we can replace it by omega. U, M, K. And then we are getting all these factors. Omega, A naught, polarization vector, H bar will cancel, imaginary unit stay, M R K sine omega t. If we remember that time derivative of the vector potential gives us electric field, then this combination of speed of light A naught and frequency can be replaced by electric field. And then everything is this E charge of the elementary charge of elementary particle can migrate inside there. And then if you put E here, it will be just matrix element of the dipole, D, MK, right? Charge times distance is dipole.
Yes.
Okay. And then U, MK. I just want to write the last equation and then we are done. So U, MK is equals minus. I lost this image. Probably imaginary unit will also go to the definition of E naught. So E naught cosine omega t times matrix element of the dipole between states M and K. Right? So we have received, we have obtained the original equation we were starting from. So potential energy, not potential, energy of interaction between light and matter is minus electric field times dipole. And we didn't, well, I did some minor errors that can be probably fixed by polishing, but we started with formal definition of light to matter interaction is due to modification of the momentum through vector potential, and we arrived to something that we are expected to know and practice as chemists. And on the way, we just enriched our background by the concepts of weak field approximation, long wave approximation, and stuff like that. I think we are done. What I was planning to show and failed to do is pictures about Aron-Bohm effect. Basically, bless you. It is a proof that there are areas of space, like if one has basically a nail, magnetic nail, between two